Chapter 7 is wrapped up by looking at some trends in several atomic properties and relating those trends to the periodic table and how the elements are laid out in the periodic table. The trends we'll look at are ionization energy, electron affinity, and atomic radius. First, let's look at ionization energy, which is the energy required to remove an electron from a gaseous atom or ion. If we take a generic element X in the gas state, then it would be the energy required to convert element X to X plus an electron. If we look at magnesium as an example of a metal, magnesium is converted into the magnesium ion plus an electron with a first ionization energy of 735 kilojoules per mole. Magnesium typically forms the magnesium 2+ ion, and we see a second ionization energy of 1445 kilojoules per mole, which is about double that first ionization energy. Now, in going from magnesium 2+ to magnesium 3+, we see a huge jump in ionization energy. This is because we would need to remove core electrons, which are bound much more tightly than valence electrons, in order to form the magnesium 3+ ion. Therefore, magnesium typically forms the magnesium 2+ ion in chemical reactions. Now, in general, as we go across a period from left to right, the first ionization energy increases. This is because electrons are added in the same principal quantum level and do not completely shield the increasing nuclear charge caused by the added protons. Electrons in the same principal quantum level are generally more strongly bound from left to right on the periodic table. In general, as we go down a group from top to bottom, the first ionization energy decreases. This is because the electrons being removed are on average farther from the nucleus as we go down a column of the periodic table. In this chart, we can examine both trends. If we look at, for example, the noble gases, helium, neon, argon, krypton, xenon, we see a drop in first ionization energy in going from helium down the column of noble gases. If we look at the elements highlighted in green, lithium, sodium, potassium, rubidium, cesium, we see a decrease in going from lithium down that group of alkali metals. Now, if we go up from lithium to neon, which would be going across the second period of the periodic table, we see an increase in general in in ionization energy. From lithium to beryllium, we see an increase. There's a slight decrease going from beryllium to boron because in boron we're removing an electron from a p orbital, which is higher in energy, and so we have this lower ionization energy. It's easier to remove that electron, which is further away in the p orbital. Then going from boron to carbon to nitrogen, we see the increase in ionization energy going across the period. There's that slight decrease again at oxygen, because in oxygen we're removing a paired electron, whereas in nitrogen the electrons are all unpaired. It's slightly easier to remove that paired electron because it's higher in energy. And then in going from oxygen to fluorine to neon, we see an increase in ionization energy again. We can see this for any of the periods of the periodic table. we could see the same trend in going from sodium to argon, or from potassium to krypton. Here we can see tabulated ionization energies for elements in period 3 of the periodic table. Again, we see a big jump in ionization energy in going from the first to the second ionization energy for sodium, because first ionization energy for sodium is removing a valence electron. In the second ionization energy, we're removing a core electron, which is much more difficult to remove. We see that same trend in magnesium and aluminum and silicon, which is a metalloid and will exhibit some metal-like properties. When we go from silicon to phosphorus, we have a big jump in first ionization energy because phosphorus is a nonmetal and tends not to lose electrons. We see chlorine to argon, again a very large jump in first ionization energy because argon is a noble gas and tends not to give up electrons. Now let's look at the next property, electron affinity, which is the energy change associated with the addition of an electron to a gaseous atom. There is some ambiguity in the literature regarding the sign of electron affinity. But in general, more negative energy equals greater energy released, which is more stable. If we take generic element X, its electron affinity is related to its ability to attract an electron and form anion X minus. In general, as we go across a period from left to right, the electron affinities become more negative. In general, electron affinity becomes more positive as we go down a group. Finally, we'll look at atomic radius. Now, atomic radius can't be specified exactly. It's like the size of an orbital. It's estimated using distances between atoms in chemical compounds. When we use covalent compounds, we call these covalent atomic radii. For nonmetallic, non-diatomics, atomic radii are estimated from various covalent compounds. Metallic atoms' radii are measured as half the distance between metal atoms in solid metal crystals. In general, as we go across a period from left to right, the atomic radius decreases. This is because the effective nuclear charge increases, therefore the valence electrons are drawn closer to the nucleus, decreasing the size of the atom. And in general, atomic radius increases in going down a group. This is because orbital sizes increase in successive principal quantum levels. So if we look at group 1A, going down group 1A, from lithium to sodium to potassium to rubidium to cesium, we see atomic radius increase. In going across that second period from lithium to neon, we see a decrease in atomic radius. Now keep in mind that it's the number and type of valence electrons that primarily determine an atom's chemistry. The electron configurations can be determined from the organization of elements on the periodic table if you know how to read main group elements versus transition metals versus lanthanide and actinides. Certain groups in the periodic table have special names which should be memorized. Group 1A, excluding hydrogen, are the alkali metals. Group 2A are the alkali earth metals. Group 7A are the halogens. Group 8A are the noble gases. Down at the bottom of the periodic table, we have the lanthanide and actinide series. That center portion are the transition elements. Now, beyond metals and nonmetals, we can also include metalloids and semimetals. The metals tend to give up electrons to form positive ions. They have very low ionization energies. Nonmetals react with metals to gain electrons. They have large ionization energies. They have negative electron affinities. Metalloids or semimetals lie somewhere in between metals and nonmetals. They will exhibit both metal and nonmetal properties depending on conditions. We'll wrap up this chapter by just talking a little bit about the alkali metals, group 1A of the periodic table, which are illustrative of similarities in group properties. The elements in group 1A are lithium, sodium, potassium, rubidium, cesium, and francium. These are the most chemically reactive of the metals. They react with nonmetals to form ionic solids. In going down the group, the ionization energy decreases. The atomic radius increases. The density also increases. The increase in density is because atomic mass increases faster than atomic radius, which means there ends up being more mass per unit volume. And the melting and boiling points smoothly decrease for this group. The most characteristic metal property we see is the ability to lose valence electrons. In reactions, these metals, lithium, sodium, potassium, rubidium, cesium, and francium, give up electrons. Therefore, they are oxidized or act as reducing agents. The nonmetals, which are combined with these elements, accept electrons and are reduced or act as oxidizing agents. The reaction of any of these metals is highly exothermic with water. It produces hydrogen gas. The reaction is exothermic enough that in many cases this hydrogen gas produced will catch on fire and can potentially be extremely violent.